Okay, so part two is about Newton's laws of universal gravitation. So we talked about Isaac Newton's laws of motion before. Now we're going to talk about Isaac Newton's law of gravitational force. So things that are in orbit are what are called free fall. Free fall is simply when an object is moving towards the Earth due to simply gravity. And what Newton figured out was that if every time you fire a cannon, if you fire it faster, it goes farther in distance. So if you can make a cannon fire fast enough, it could go around the Earth, literally fall around the Earth. Okay? So things in orbit are going fast enough where they're going out and down at a rate where they're going around the Earth in orbit. Okay? So the curvature of the Earth will cause a cannonball to continue falling if it's going fast enough. Okay, so when an object is in orbit around the Earth, like it's like a satellite, it's going fast enough where its horizontal speed is fast enough to not let it fall completely back to Earth. So if an object in orbit wants to come back to Earth, they simply slow down, then they fall down. Okay, so the centripetal force that holds a planet in orbit is the same that pulls an apple towards the ground or keeps a spinning thing on a string. It's a gravitational force. Okay, gravitational force is the mutual force of attraction between particles of matter. It acts between all objects over a distance. You don't have to touch to have gravitational force acting. Okay, so gravitational force depends on the masses of the two objects and the distance between them. Okay, but the forces acting on one are equal to that of the other one due to Newton's third law of motion. Okay, so Newton created this equation that says it's what's called Newton's law of universal gravitation. The gravitational force between objects, and the same forces on each object, is equal to a constant times the product of the masses divided by the distance between them squared. So the masses are proportional to the force. If the masses double, so does the gravitational force. However, the distance between them is what's called an inverse square relationship. So if you double the distance between, your gravitational force decreases to 1 over 2 squared, or 1/4 as much. So the farther you get away, the much less gravitational force you have acting between objects. Okay? And the big G here is called the constant of universal gravitation, and it's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay. So this equation is something you're going to have to practice, and you're going to get some practice on the formative assessment below the video. Okay, so the gravitational force that two masses exerted on each other are always equal and opposite because of Newton's third law of motion. Okay, the Earth-Moon system is an example, as is the Earth and Sun. The Earth and Sun have equal and opposite forces. Okay. So the moon and the system orbit the center of the mass of the Earth system. Because Earth has a much greater mass than the moon, the center of the mass actually lies within the Earth. But they orbit around that main point. So like this. But again, this is the force acting on the moon from the Earth, is equal to the force acting on the Earth from the moon. Okay, they're equal and opposite forces. And this is what keeps the moon orbiting the Earth. And we can figure out the Earth's rotational rate. We can figure out their centripetal force, tangential velocity, all that stuff because of the math gained in the first video. Okay. So tides are all about Newton's universal law of gravitation. Okay, they're partly due to the gravitational force. Okay, they result in the difference between their gravitational force at the surface and the center. Those differences create the tides that you've all seen. Okay. Now, we can find the value of the universal gravitational constant in the Earth's mass. A guy named Cavendish did this. So when two masses, when they know their distance between, and if they know their gravitational force, Newton's law of universal gravitation can actually find universal gravitational constant. Okay, once the value of g is known, then the law can be used to again find Earth's mass. And what they found is that the gravitational force is what's called a field force that acts over a distance. Okay, gravitational field strength, acceleration due to gravity, is force of gravity divided by mass, Newton's second law. The gravitational field, our acceleration due to gravity, is a vector with magnitude g that points in the direction of the force of gravity towards the center of the Earth. Okay. So with this, if you know the force of gravity between the objects, you can figure out how fast it accelerates. So you can actually find little g from big G. Okay, and again, weight of an object is its mass times the gravitational field strength. Okay, but because it depends on the field, on how close you are, the weight can change with your location. So your weight is mass times acceleration due to gravity. We rearrange F equals ma. A is our acceleration due to gravity. Is really force divided by mass. The gravitational force from universal gravitational constant is gravitational constant times the products of the masses divided by the r squared. And if you notice, me is the Earth, so like the big mass. So these two little masses, which is the mass of an object in orbit, or in case of you on the surface of the Earth, these cancel. So our acceleration due to gravity can be found by taking the gravitational constant times the mass of the Earth divided by r squared. We'll talk a little bit more about this in class. Okay, but on the surface of any planet, the value of acceleration due to gravity, as well as your weight, will depend on the planet's mass and radius. The planet's mass and radius, your mass is really insignificant. Okay, and that is the end of this video. Make sure you answer the questions on the Google form, and be sure to ask questions in class, and we'll see you in class.